Okay. So, for a water molecule, basically what we're doing is deciding, in the case of each of these forces, does it apply to water? So, let's just go down the line. Are there dispersion forces in water molecules? Yes, there are dispersion forces in everything. So, yes, we are going to have dispersion forces always. If you ever get asked to list the forces that are present on a given molecule, then dispersion forces is always on the list. Do we have dipole-dipole interaction? So when are, this is all molecules. When do we see dipole-dipole interaction? What kinds of molecules have dipole-dipole interactions? Permanently polar molecules. Is water permanently polar? Yes. So are we going to have, I've got this arrow pointing up towards the oxygen, right? So are we going to have dipole-dipole interactions if I have two water molecules? Yes. So if on your notes page you don't have all molecules under dispersion forces, and if you don't have polar molecules under dipole-dipole interactions, you might want to add that to your notes. What about dipole ion interactions? Are we going to have those? Sydney, you're shaking your head. How come we won't have those? Yeah, there's no ions here. Water has partial charges, but that's not the same thing as having an actual ion. That is not the same thing as being positive or being negative, okay? This is being an ion. This is having partial charges. So the deltas give us a partial charge. A full positive or negative would give us an ion. And we don't have any ions here. Our water molecules are all neutral. So we are not going to have dipole ion interactions. What about hydrogen bonding? Are we going to have hydrogen bonding here? I've got some people nodding yes and putting thumbs up, and some people saying no, no hydrogen bonding. What needs to be present in order to have hydrogen bonds? Yeah, there needs to be polarity, but there needs to be a specific kind of polar bond. Yes, Sydney? Uh-huh. Brayden, want to help out? Oh, I'm sorry, you got it. I saw you with your hand up there. If I have any of these bonds, hydrogen and oxygen, hydrogen and nitrogen, hydrogen and fluorine, I have hydrogen bonding. Okay? This is a subset of dipole-dipole, right? The same, we don't have something new and different with hydrogen bonding. We just have something stronger. Okay? So it's a stronger version of dipole-dipole. Why is it stronger? Yeah, Brayden? Exactly. So these fluorine, oxygen, and nitrogen are the three most electronegative elements on the periodic table. When hydrogen bonds with any of these three, the difference in electronegativity is going to be really big, which means the partial positive on hydrogen is going to be really big. Okay? And that is going to make the force of attraction stronger. The stronger the charge, the stronger the force of attraction. Back to our Coulombic forces paper. So even with just a partial charge, the stronger it is, the stronger the force of attraction. So this hydrogen that's very partially positive is going to have a very strong attraction to the oxygen of another water molecule that is partially negative. Okay? Now, if I had said, sorry, let's answer number 2 first. If there's more than one force, which there are, we've checked 3 of them, which one is the strongest? Yes. Close. Yes, dipole-dipole, but specifically the subset of dipole-dipole. The hydrogen bonds are stronger than any other dipole-dipole interactions, okay? So we can have a polar molecule that doesn't have hydrogen bonds that still has dipole-dipole interactions. In this case, the hydrogen bonding is a dipole-dipole interaction, so it's not wrong to say that that's the strongest. It's just that what I want is that the hydrogen bonding is the strongest. So if you're asked for the strongest force, if there's hydrogen bonding, that's what it is. I'm not going to ask you a question on a quiz where we have both dipole ion and hydrogen bonding, and I want you to somehow figure out the difference in strength between those, because they overlap a lot. If you look at the flow chart, they're kind of in the same place, okay? Here we don't have that, so this is definitely the answer for the strongest. If I did not say the water was pure, if I said tap water, would anything change? Okay, what would be different? Yeah, there'd be other stuff in there, for sure. Would we change anything about the presence or absence of different forces? Think about, remember the light bulb? When we stuck the wires in distilled water, pure water, did it turn on? No, did not. We got nothing with pure distilled water. When I filled the beaker with tap water, did the light turn on? Yes, because there are ions in tap water. Some of the metal ions from the pipes, some traces of different salts, whatever happens to be in the supply, right? And people pay a lot of money for those ions. If you get fancy spring water in a bottle at the grocery store that tastes a certain way, you're paying for the ions in the water. It tastes different from distilled water because of the minerals in it. So if I said tap water, then we would have all of these forces present. But if I say distilled water, it's just the 3. Okay? So what I want to do today is talk a little bit, go over hydrogen bonding a little bit more specifically, and give you some examples of when you do and don't have hydrogen bonding. And that'll be the worksheet that you picked up. And then I'm going to kind of stop there for a second and talk about the effects of these intermolecular forces on boiling points and what that means when we actually have chemicals in front of us, like in a jar. What does it look like? So to go back to our hydrogen bonding slide, we were just talking about this is a very strong force of attraction between a very polar hydrogen and another polar molecule. We only have hydrogen bonding if we have HF, HO, or HN bonds. We don't necessarily have hydrogen bonding just because there are hydrogens. The hydrogens have to be bonded to one of those 3 for us to call it a hydrogen bond. I could have HCl. That's a little bit less polar than HN and falls out of our definition of hydrogen bonding. Of course, everything is a continuum, so that's still going to be a very strong dipole-dipole interaction, but that's outside of the limits that we're putting on calling it hydrogen bonding. Why are these drawn with dotted lines and dashes there? Why isn't it just like this? Yeah, they're not the same molecule. Solid lines generally indicate bonds, okay? A dashed line generally indicates an IMF or other source of attraction, okay? So when you are drawing out, which you will have to do, the attractive forces, trying to connect atoms of different molecules that will be attracted to each other, please use the dotted line, whatever version of it, dotted line, dashed line, whatever you can make so that it's clear that it's not a solid line. because these are not actually bonded together. They are attracted to each other. Okay, so your intermolecular forces practice sheet that you picked up today. First thing you do, please write your name on the top. I got a lot of those Lewis structure and polarity sheets that, because I didn't put a place for your name, nobody put their name on it. So I'll be checking in with you guys tomorrow to see who the no-name ones were. So please put your name at the top of this. The sheet that we filled out yesterday is yours to keep. Hang on to it until we finish this unit, which will go into next semester, and some of you are going to a different classroom, but we are all doing this sheet. So you will either take it, you'll take it with you. When you, well, we haven't all done this as the notes sheet, but we are all doing this worksheet that you picked up today. So this will be an assignment on your third quarter gradebook. It will not go on this quarter's gradebook. But regardless of whether you're in this class next quarter or not, in my class next quarter or not, we're all still doing this. So this is your keep with your notes on it. This is your finish and turn in at some point next week. So what you're being asked to do is draw a representation of hydrogen bonding. If there is a possibility of a hydrogen bond, of that intermolecular force, then you would draw it with the dotted line. So make sure that you're using dotted lines. That's a terrible example, but it's harder to do with the pen on the board. I would recommend writing up at the top what the conditions are that are going to give us hydrogen bonding. What do we need to have a hydrogen bond? Yeah, it is a form of dipole-dipole, but what am I looking for in these molecules to decide whether or not they're going to have hydrogen bonding? If they're polar, yes, but specifically for hydrogen bonding, we're calling it hydrogen bonding. Yep. I would write this at the top to remind yourself that that's what you're looking for. Now these molecules, some of them are a little more complicated. They're nice little organic structures with lots of carbons and hydrogens. So all hydrogens all over the place. That does not mean that you're going to have hydrogen bonds all over the place. So looking at A, do you see a place where we could have hydrogen bonding in the molecule? Is there the presence of an HF, HO, or HN bond in the molecules given? Yes, Gracie's nodding her head yes. There's one here, there's one here, and there's one here. Okay? Now, those are going to be the ones involved in the hydrogen bond. Okay, in the force of attraction. There's all kinds of other hydrogens around here. Are they going to be involved in hydrogen bonding? No, why not? Why are these not going to be involved in forming a hydrogen bond? Yeah, Jose? Yeah, they're connected to carbons. That is a nonpolar bond. If you look at this and you say, oh my God, there's so much going on here, I have no idea where I'm going to draw those dotted lines. One thing that you might try, and it's not something you have to do by any means, but it might be helpful for some people. Just find all the hydrogens that are bonded to carbon and cross them out. And say, that's not hydrogen bonding. That's not hydrogen bonding. None of those hydrogens can be a part of hydrogen bonding because they're not bonded to the oxygen. They're bonded to carbons. So that narrows the field considerably, right? Now we have a little bit more, it's a little bit more obvious where our forces of attraction are going to be. So this hydrogen here that's bonded to an oxygen can be involved in forming a hydrogen bond, a force of attraction with another molecule. Where on the other molecules will it be attracted? Where will I draw? Yeah, exactly. I'm not going to draw This is not a hydrogen bond. No. That's between two hydrogens, but that is not a hydrogen bond. The hydrogen bond is between the polar hydrogen at the end of the oxygen and the oxygen on another molecule. That's the force of attraction that we're looking at, okay? And however you can make that look like a dashed line and be connecting those two is fine, okay? Are there any others? Come on up and show me some of the others. Other side. Yeah. All right, so there was another one over here between these two molecules. Any others? Yeah. This O? The hydrogen. This one? Sure. Can have that attraction. You mean this here? Yep. Could have that. Anything else? Here? Down? Right here? Yep. Okay. You don't need to have all of these. I need you to have at least one that connects each molecule to each other molecule that would be involved in the bonding. Okay? You don't have to do all of the crosswise ones, and you don't have to do every permutation like this oxygen and that hydrogen. It's just the ones that are close enough that they would probably be attracted to each other and force these three methanol molecules to hang out together. Yes? Those are two different molecules. No, not necessarily. So, since we're there, let's talk about B. So, I've got an OH here. So, I've got my very positive hydrogen on the end of that bond. That is looking for something negative to be attracted to be very strongly attracted to. Is there anything that might have a partial negative charge on the other molecule that could give an attraction? Yeah, the oxygen. This carbon-oxygen bond is polar. Remember? Carbon and oxygen is polar. Also, oxygen's got these nice juicy lone pairs there. And hydrogen is going to be like, oh yeah, I want some of that. Let's hang out. Okay. So these two molecules will form a hydrogen bond between them because of this hydrogen. Not because of the oxygen, but because of this hydrogen and the presence of polarity on the other molecule. So they don't both have to have OH or OF or HN in order to form that kind of bond. Just have to have at least one of them with that very, very, very positive hydrogen. Okay? So I'm going to give you, if we finish before the end of class, I'll give you a little time to work on this today. But I want to change gears a little bit. If you have your notes sheet from yesterday, you might want to jot a few things down on that. I didn't want to give you a whole nother page of, a capture sheet because there's just little things here, and we'll go over it again you'll go over it again with whoever you're with next week. So tomorrow, if we have school, tomorrow will be a work day, catch-up day. Depending on how that goes, Friday might be a lab, or we might move the lab. I think most of the classes are going to move it to Monday. If you are in a different class next semester and you didn't get a chance to do the lab because your new teacher had already done it before the break, I'll have things set up at lunchtime. You can always come in and do the lab at lunchtime. Yes. Circular. Oh, you mean circle this together? Like this? Oh, like this? Yeah, you could circle that if you wanted to. It just makes it a little busy. Is that what you're asking? Okay. Yeah, you can, or you can like, highlight this if you have a highlighter or something like that. Feel free. As long as I can see the dotted line between that hydrogen and whatever else it's being attracted to, that's fine. Okay. I wanna, because I know some of the other teachers have started talking about this already. I want to talk a little bit about the effects that these intermolecular forces have on molecules aside from water. We've talked a little bit about how those strong hydrogen bonds participate in that really strong surface tension of water like we saw in the space station video. And you're going to see more of that in the lab. But there's also another physical property besides surface tension that is very strongly affected by intermolecular forces, and that's the boiling point and the melting point, but we usually talk about it in terms of the boiling point. So let's review our states of matter before we go any further. There are more than 3. There's somewhere between 6 and 8 or whatever, depending on what physicist you talk to about it. We're only concerned about 3. So solid, liquid, and gas. You should all be familiar with all 3 of those things from your day-to-day life and from previous science classes. But let's just quickly review what the differences are between solids, liquids, and gases, because it's relevant to what we're talking about with the intermolecular forces. So our solid materials are going to be tightly packed. So usually they're going to be more dense than a liquid. So they're tightly packed together. There is a fixed volume. It doesn't expand or contract, not much anyway, and a fixed shape. If I have a cube, it's going to be cube-shaped, no matter whether I put it in a shallow bowl or a tall graduated cylinder or just on the desk. It's going to keep the same shape no matter what, as long as it is still solid. So we've got the molecules or atoms or particles. Well, I'll use particles because that's more generalized, includes molecules and atoms. The particles are not moving around. They're not freely moving, but they are moving a little bit. So there's a little bit of vibration and rotation happening. So everything that's not at absolute zero is moving just a little bit. Every molecule in this tabletop is moving. It doesn't look like it's moving because we're not looking at that atomic level, but it is. Every atom is vibrating just a little bit. Every molecule is vibrating just a little bit, even in a solid. But they're not moving relative to each other, right? They're in the same fixed position, fixed shape or position. So all the particles have a fixed position relative to each other, but they are moving within that position. And that movement is what we call kinetic energy. And that's what we measure when we use a thermometer. We're measuring the average kinetic energy, how much the molecules are moving. We call it temperature. It's essentially average kinetic energy. In a liquid, we have usually less dense. We have fixed volume, but freely moving. The molecules are moving around, but they're staying together. They're not just all evaporating out. If I open up my water bottle, the water isn't all going to come out right away. It will eventually if I leave it open for long enough, but basically it's just going to stay there as a liquid. It's not going anywhere, except in my mouth. So we've got freely moving particles, but they're still hanging together. And then a gas is a situation where all the particles are separated. So no fixed volume or position. And the gas is going to expand to fill the space that it's in, which is why if somebody puts on a little bit too much aftershave after gym class, you can smell them coming all the way down the hall, right? Because those molecules of perfumes and things like that are designed to be volatile, to become gas particles that can then travel all over the place and basically fill up the whole hallway. All right. So how do we turn a solid into a liquid? Not quite. Melt it. So the transition from a solid to a liquid is called melting. Ice to liquid water. Any solid substance to its liquid form is called melting. The other way, it's called freezing, right? We'll talk more about that, sort of the different names of the different transitions. What do we call it when we take a liquid and turn it into a gas? That's the boiling. How do we get something to go from solid to a liquid? How do we get it to melt? Yeah. Yeah, we heat it up. We increase the temperature. Okay? So as the temperature increases, we go from solid to liquid to gas. The point at which we transition from a solid to a liquid or liquid to a gas is particular for every substance. So for water, this is 0 degrees Celsius or 273 Kelvin. We'll use both of those later. Boiling, anyone know what the boiling point of water is? Yes, 100 degrees Celsius or 373 Kelvin. Okay. Something else might melt at a different temperature. Wood probably melts at a different temperature or boil at a different temperature. So different substances are going to have different melting and boiling points, and that's called a physical property. It's something intrinsic to the substance itself. What is it that's keeping those liquid molecules in my water bottle from just going off and becoming a gas at any moment and coming out of the bottle? Yep, it's a lower temperature. What does it mean if they're at a lower temperature? What are they not? Yeah. Right, they're not moving enough. But why do they have to move to become a gas? What's holding them together? Yeah. It creates what? Yeah, so we're adding energy. Why does it take energy to go from a liquid to a gas? Yep, heat, energy. What else is happening at this transition from a liquid where the molecules are hanging together and a gas where they're completely separated? What are we breaking? Not bonds. Yes. Intermolecular forces. Okay, so in order to go from a liquid where the molecules are all hanging out together to a gas where they're all separated, we need to break apart those intermolecular forces. We have to increase the energy of the molecule enough that it breaks out, okay? And the same thing is happening at the solid to liquid transition. What's happening here is some of the intermolecular forces are breaking up. As we increase the heat and increase the movement of these particles, it's going to counteract some of those relatively weak forces that are holding these molecules together. If I boil water, it's still water. I haven't broken the bonds. It's still H2O, whether it's in a cloud or in my water bottle or in the ice machine. It's still H2O. The chemical has not changed, just the phase, just the state of matter. And it's changed because I'm changing the relevance of the intermolecular forces. At high temperatures, they're not strong enough to hold the molecules together when they're moving that fast. Okay. And like I said, different substances have different melting and boiling points. Also there's a difference between boiling and evaporation. Both things happen in all substances. Boiling is when we're adding heat to make the transition happen, to make the phase transition happen. Evaporation is when we just randomly have some molecules that are high energy enough close to the surface to just release those intermolecular forces and go off and become gas molecules. So that's going to be a lot slower than boiling. So solid substances are experiencing stronger intermolecular forces. Gaseous substances are experiencing weaker intermolecular forces. And the sort of textbook case of this is our halogens. So in group 17, we have fluorine, chlorine, bromine, and iodine. And all of them exist as diatomic molecules, as F2, Cl2, Br2, I2. If I draw an I2 molecule on the board, is that polar or nonpolar? Nonpolar. These are two of the exact same atom, the same electronegativity, no asymmetry here. They should have equal pull on the bonding electrons. So this is a completely nonpolar molecule. So all of these are nonpolar molecules. What force is going to be present if I have a bunch of I2 lying around? What intermolecular force is going to be there? Brayden? What? Yeah, only the dispersion forces. It's the only thing that's acting on these. These are nonpolar, only dispersion. So you might think that they would all be gases, because there's only this very weak intermolecular force potentially holding them together, so they should all just, fly out of wherever they are and exist as a gas. But they don't. Fluorine does, and chlorine does. They both exist as gases at room temperature. And bromine, though, is a liquid at room temperature, and iodine is a solid at room temperature. So how do we have these different states of matter at the same temperature when we have these not completely nonpolar molecules? It's not because of polarity. It's because the dispersion forces are stronger when we get bigger. Bigger molecules, more electrons, more possibility of that temporary dipole happening and lasting just a little bit longer. And therefore the molecules sticking together just a little bit more tightly. Or get the molecules being a little stickier. Chlorine and fluorine are very small. Their molecular weight is under 100 atomic mass units. That's basically just adding two chlorines together, adding two bromines together. We'll get to that next semester. Yeah. Yeah. So as the size increases, and I'll post these slides, the boiling point also increases. Okay? So we go from fluorine with a boiling point of 85 Kelvin, that's like minus 200 degrees Celsius. Fluorine's going to be a gas pretty much anywhere, unless we compress it or have some kind of special circumstances that can take it down to below 85 Kelvin. Chlorine, 238. That's about 40 degrees below zero. So 0 Celsius. So that's also going to be a gas at room temperature and at much colder temperatures than room temperature. Bromine, 332. So that's above room temperature. So that's where bromine's going to be a liquid. It's It's not going to be a gas yet, but it is going to be a liquid, or it's not going to be solid yet. Iodine, the boiling point isn't until 457 Kelvin. So we're way, way above the boiling point of water for iodine, which is why iodine is a solid. However, if you look at these pictures, you can see there's kind of like a little bit of gas coming off of the iodine. There's these crystals, but there's a little bit of something coming off it. Same thing with the bromine. It's liquid down here, but there's a little bit of brown stuff coming off here. That's because they evaporate a lot faster. And in the case of iodine, we have some sublimation going straight from the solid to a gas. And that's because they're nonpolar. So they evaporate quickly, but their boiling points increase with the size of the molecule. The boiling points are also going to increase, and I'll come back and review this, but boiling points are also going to increase with the polarity. So if we have a molecule of about the same size, methane, chloromethane, and methanol, pretty similar sized molecules, the methane is completely nonpolar. It has a boiling point of negative 161. Chloromethane, just replace one of those hydrogens with a chlorine, now we have a polar molecule. Now we have dipole-dipole interactions. And that increases our boiling point to negative 24. So we made a significant increase in our boiling point. Change out the chlorine for an oxygen and a hydrogen, still close to, or actually even smaller in molecular weight to the other one. And now we have hydrogen bonding. And now we have methanol existing as a liquid at room temperature and not boiling it until we get to 80 degrees Celsius. So higher boiling points if we are more polar, holding the molecules together more strongly, or if we are a larger molecule with just dispersion forces. So even just those weak dispersion forces are enough to make iodine a solid. All right, so we call them weak, but they're pretty significant. All right, guys, hopefully see you tomorrow. If not, I will see you on Friday. Thank you. Yes.
Correct. Would the chlorine be weakly attached to the
Yes. The chlorine is going to be surrounded by water molecules with the hydrogens pointing towards the chlorine. And the sodium is going to be surrounded by water molecules with the oxygens pointing towards that. Yep.
So did I draw it? It wouldn't exactly would the oxygen still be attracted to the hydrogen?
Yes, it would. You would have both your hydrogen bonding and your ion dipoles happening in that situation. But what we're usually looking for with this is something like that, where you're showing that it's, because just one,
Oh, because it's just so much water.
yeah, because just one of them isn't going to be enough to separate these two. But we've got all these waters, and that's enough to separate them out and get them solvated. But what you drew is not incorrect. That's it. You're correct about that.
So if I put a drop of water into a pile of salt,
Uh-huh.
then nothing happens?
No, there's still
Does the water
millions of water molecules, and yeah,
Oh,
in a drop of water. Okay.
but if I put it in a pile of salt.
Right. Yeah. Then
So-
only some of the salt is going to dissolve a little bit, and then the rest of it's going to stay solid because there's just not enough. That's also partly a location thing.
Yeah.
It just doesn't get to all of the salt. If you had a pile of salt and you put water just to cover the salt, eventually it would probably all dissolve if you waited long enough or had it warm enough. But that would be an interesting experiment, actually. Like how much salt could you dissolve? And that's actually, solubility is a thing. It's another physical property. How much can you dissolve in a certain amount of water at a certain temperature? So, great questions. Hi.
I'm wondering, if I'm missing anything.
Let me, right, hang on.